Welcome everyone, and thank you for joining my session about deploying AI inference using network addressable processing units. I'm going to drop you from the application level that you heard about in the previous lecture down to the infrastructure. So hope it's not too big of a fall. I'm personally, I'm a system and semiconductor guy. So seeing where the industry is going is really exciting. Building supercomputers that can train foundation models in a matter of days. But I'm actually here to talk to you about inference and not the training of models. The purpose of my talk is to zoom in into AI deployment, taking real models that were trained to help with sentiment analysis of a caller that use a voice bot, or a drive-through in McDonald's that handle your orders automatically. When we look on the market, we're actually dividing it in three different technologies: the computer vision technology, the natural language processing, and also automatic speech recognition that coexist, and the recommendation engines. And the opportunities are enormous to scale inference usage. Computer vision can help us manage smart cities, manage the traffic, anomaly detection, theft prevention. In manufacturing, we can detect anomalies and make sure that they're not shipped into the market. In natural language processing, we already use it in financial services, customer service, digital assistant like Alexa and Siri, and recommendation engines really help us drive social networks, marketplaces forward. If I look only on, just taking as an example, the financial service, and you zoom in into the different use cases that were developed and are being developed, from credit decisions to fraud detection, process automation, risk management, algo training, and this customer service and chatbots and voice bots in call centers, the possibilities are huge. Many companies are driving usage of deep learning processing to real usage, improving business, improving customer satisfaction. But still, many of these AI possibilities cannot be realized today. And the main reasons are that existing AI solutions are built for training. These are large, high-performance compute, multi-rack systems that cost a lot of money, consume a lot of power consumption, and the complexity of programming them is very, very high. When you zoom into inference-specific servers, they're still using the CPU-centric architecture. So the CPU is in the center, and deep learning accelerators are added to the system, creating all kinds of bottlenecks that result in high cost and high power consumption. But last but not least, the complexity of programming, and it's not only developing models, it's deploying them on GPU servers or ASIC servers, connecting them to the other system, to the storage, handling the networking, and making sure that we consume those GPUs that we invested so much in them to 100%. And all these are kind of pushing back companies, mid-size and small size, and even large companies that doesn't have the R&D resource that Facebook, Amazon, or Apple has. So let's go back to the customer support example with NLP. When you look on, when you're trying to bring a new solution that will improve the complexity and the cost and power consumption, you have to understand the system. And I brought here the NLP because it's a very good example of two extremes to the same problem. Today, most of the chatbots that you use today have a trained model for a specific use case, for healthcare, or for customer service in an insurance company, or for other usage. And then when multiple clients are using NLP systems, there's a front-end system that will need to get all the requests from the different clients, identify what type of client they are, and then invoke the right model to be used. So this is a certain system aspect when you analyze the end-to-end data commute, networking, and processing that is needed. On the other hand, everybody is hearing about GPT-3 and DALL-E 2 and the foundation models that kind of take all these use cases and train a huge model to handle all of them at once. But then you need to do all kind of parallelism, because if you try to run a foundation model on a single GPU, it will take us minutes. We cannot drive chatbots that the response time is minutes. You have to go below a second. So when we look on these, the task-specific models, the small and medium-sized, and the huge foundation models, and you understand this, and you analyze the system complexities, here you need to do all the complementing model processing. You train the model in PyTorch or TensorFlow, and now you want to run it on a deep learning accelerator, but the deep learning accelerator doesn't support all the operands you use. So now it's on the customer or on the developer to partition it, what will run on the accelerator and what will run on the CPU. You need to handle the model loading and switching. Remember this system that takes requests from all kinds of users and then identify what type of user and what type of model to invoke. This system needs to work very fast, and it runs on the CPUs that host the deep learning accelerators. And then there's quality of service. I need to run queue management for each one of the clients, scheduling, load balancing between my deep learning processors, and I need to handle the data movement and the data processing. If it's an audio recording, I need to run audio codec before I can run the NLP model. Now, when you go to the huge model, on top of all these, you need to handle the model parallelism. You just broke this huge model to many deep learning accelerators. How do you commute the data, the intermediate results between the different models, the different deep learning accelerators? And then how do you do the intermediate data processing, the map reduce or whatever is needed there? So this is where NeuReality comes in. We started from mapping the requirements for these computer vision use cases, language processing use case, and recommendation engines. And when we analyze the system data flow, the networking that is needed, the latency requirements, and we came up with a new type of architecture that is handling the end-to-end experience. We had to develop a new type of a chip that we call network addressable processing unit to host those deep learning accelerators in a better way, lower latency, and much lower cost. And in order to provide a simple way to use them, we also invested in 3 layers of software that I'll show you that simplify the development, the deployment, and the runtime itself, the management of the systems. And all of them are exposed through very simple to use APIs for the data scientist, for the DL engineer, and for the DevOps engineer. We're focused on data center to near edge. We're not covering the edge, the IoT devices, or the inside the automotive. So we are installed in any public or private cloud. We can be on-prem in a retail shop or a bank branch or a place, a manufacturing line, and near edge in 5G base stations and other gateways. Any place that you need to install a very efficient server to handle the high performance inference requests. And this is a glance on how the architecture looks. So it's not the CPU hosting all the deep learning accelerators. Each one of the deep learning accelerators is connected to the network through one of our chip. This is the network addressable processing unit. And now you get a system that was purpose-built for inference. All the data paths that is bringing data and processing data for the deep learning accelerator are hardening and running in hardware instead of in software on CPU. You get ultra scalability because the more DLAs you put, the more connections you have to the network, and there's no single point of failure, you achieve, when I say here the lowest cost and power consumption, I talk from the system level. It's the same deep learning accelerator that you use today, but now you can utilize it to 100%. You hardened everything, so all the data passes in hardware, so you can push up to 13x better AI operations per dollar invested, and up to 12x on AI operation per watt. So you save on the capital expense of buying these servers and the operational expense of the power delivery and hosting them in terms of density, power cooling, and all this. And of course, there are zero system bottlenecks. So you leverage the hardware that you invested in to its 100% utilization. What is more interesting is how do we make it easier for you to use this hardware? Because providing heterogeneous compute solutions, by the way, I want to be mindful of the time. It's one, okay. Is just one end of the things, providing a good hardware with low total cost of ownership. How do we let software developers use it? So we invested in 3 layers of software. The bottom one is the full model support. So if you have a deep learning accelerator connected to NR1 on the hardware infrastructure, you don't need to know how to partition what's going to run on our audio codecs or video decoders or vector DSPs or CPUs or deep learning accelerator. The model support will take your trained model, PyTorch, TensorFlow, whatever, and will create a compute graph out of it and partition what will run on each one of the processors and how it will be generating the artifacts for the AI hypervisor, a piece of hardware that handles the quality of service, to run this pipeline through the hardware. So we make it agnostic to the developer that need to partition it. Of course, he can give hints to the compiler, but it's mainly automatic. The second one is to handle the pipeline. If I'm doing face recognition, I need to decompress the image, do JPEG decoding, resize the image, quantize it. All these parts of pre-processing and post-processing to the model that was trained are handled by NR1, by the processor that we developed. And the pipeline support in the software will handle this partitioning and deployment. And last is the interface you get, the service. How do you connect to your MLOps or DevOps, Kubernetes, VMware, whatever? And this is the piece of software that we provide, which is called the NR server. That is your endpoint, your TCP endpoint that you communicate with, you provision through it, you orchestrate through it, and it handles the last layer that connects it to your system. In terms of hardware, we have the prototype today, and in 2023, we're going to introduce the first chip to the market. The first prototype is an FPGA base that you can see in our booth. It was designed together with AMD. So we're actually connecting our IP to their deep learning accelerator inside the FPGA. The second one was designed together with IBM. The deep learning acceleration engine that we use is from IBM. And this is a PCI form factor that can connect to any server you have. And it's also directly connected to the network. It doesn't overload your CPU in the server. And the last one with the highest density is the NR1S. This is the AI-centric server with 10 NR1 plus DLAs, highest density, highest performance, lowest latency, and the best total cost of ownership that you can get. A glance into what is the chip. The chip is, first of all, connected to the internet and hosting any deep learning accelerator chip through PCI interface. It has a very high bandwidth memory interface. The AI over Fabric network engine is the piece that connects to TCP or RDMA, or whatever you use in your data center. And then we have the AI hypervisor that offload all the queue management, scheduling, and sequencing to hardware. It leverages a heterogeneous compute environment, the deep learning accelerator, of course, the audio codecs and the imaging and video codecs, and the last resort is the ARM general purpose CPU that will manage all the leftovers that cannot be offloaded to high-performance parallel compute processors. So I want to invite my dearest friend from IBM, Mukesh Kar. He's the vice president of the hybrid cloud in IBM. I'll start with a quote from Sarah Ban Britha that she said that the world needs dreamers and the world needs doers, but above all, the world needs dreamers who do. And I think Mukesh is exactly that. He leads the development of AI acceleration and quantum machines and all kinds of things in IBM. And I want him to share with you what they do for foundation models and NLP.
Great. Thank you, Moshe, and thanks for your partnership. And I'm here to share with you. I represent IBM Research. As you know, IBM Research is one of the oldest. It's more than 70-year-old research organization which focuses on enterprise IT. And our biggest customer in enterprise IT is the financial services industry. So when the world of AI started to become bigger and bigger and bigger, we started to understand what is the math behind these AI computation, and how do we develop what is the right algorithm and right chip technology that can really accelerate AI workload. So we started working on a technology called reduced precision computing, where essentially, and we at IBM Research pioneered this technology and wrote very first paper where can you use 16-bit instead of 32-bit for AI computation for the same accuracy. Accuracy has to be the same. And we started to work in that. That's an innovation both in terms of math as well as algorithm, so that the model can converge, but you're using less number of bits. And as you can imagine, if you use less number of bits, you quadratically improve speed or you reduce power. So, you go from 32 to 16-bit, you are improving everything by 4x. And as you can see, for both training and inference, we have been systematically making progress. And very recently, we've demonstrated use of 4 bits for training and use of 2 bits for inference. That's a very strong roadmap, and that will give you thousands of times improvement in performance or reducing cost or reducing power. And we have a long-term roadmap. We are driving towards 2.5x improvement every year at the fundamental level. But as Moshe said, my job is not just to do fundamental math and research, but actually build product. Because we are in the business of shipping machines. We build the IT for enterprise. We build IT for financial services. We started to implement our low precision computing in 14-nanometer technology in 2018. We launched AI Hardware Center, and we are very proud that NeuReality is a partner with us in AI Hardware Center, where we have many companies who are working together. And then last year, we introduced use of this low precision core into our microprocessors called Telum. And then we built this system, IBM Z system, which essentially runs all the financial institutions in the world. That system uses the same core, the low precision core that I described earlier on. It really provides now very low latency in transaction AI inference capability that is now implemented into this system. So now you start to see that goes from concept to actually building and shipping product. And going from there, I'm very excited that we are very proud to be partnering with Moshe and NeuReality. The exactly same core that we built in 7-nanometer technology and implemented it in our microprocessor is now being scaled further, because the things like foundation model, the model size is big. You cannot survive with one core for inferencing. So we built two areas that I'm describing. From an IBM, we built a 32-core SoC PCIe card that you can see over there. That's an AIU, or artificial intelligence unit, that we have produced, which is very flexible, that can be put in as a PCIe slot in any system in cloud, as well as the same core is used by NeuReality in their NR1 chip, which Moshe described very well. So thanks, Moshe, for your partnership.
Mukesh, I just want to ask you one more question. When we talk about foundation models,
yes,
and where the world is going with huge models, what's your vision on how the development we do together will really help to make it deployed in low latency and real life use cases.
That's very important and great question. For financial industry and for enterprise workload, two things are very important. One is low latency, as you mentioned already. We cannot have your fraud detection or your approval of your loan waiting for 5 minutes because there is an AI model running somewhere in the cloud. So we want to make sure that as we develop this technology, we are providing low latency. Second, what low latency requires is not a general purpose CPU or general purpose GPU hardware. It requires specialized hardware. So we need to combine both of those, low latency and specialized hardware, and on top of it, putting the enterprise quality. Because we are not in the business of identifying cats and dogs. We are actually in the real business of financial services industry. And being able to partner and being able to develop technology where foundation model can be inferenced in an enterprise IT world is really critical. And that really benefits us to develop technology as well as our clients in the financial industry to be able to leverage this massive capability that foundation model has created for us.
Thank you. Thank you so much
for
joining me.
Thank you very much.
And I can't wait for what's coming next. So our vision is to make AI easy, AI deployment easy. With the NAPU that includes the deep learning processing capabilities from IBM and our surrounding system components, topped with the 3 layers of software, you can get it in a PCI modules to install in any one of their servers, or in a full-blown highest density inference capability. What you will experience is that it's easier to develop. It's easier to take your models and compile them to run on this new hardware. It's easy to integrate into your systems because we had been analyzing how to connect to all the MLOps out there. So even if you're using a proprietary solution, we can probably quite easily add an abstraction layer and convert these APIs between them. It's easy to deploy and run it. And very importantly, it's easy to scale your business, because going from one DGX server serving a pilot program to having millions of users or millions of minutes a day being analyzed using NLP technology is a big jump. You need to cover a co-location solution or a cloud solution, and if it's on-prem, it's even a bigger problem. So density, cost, power consumption are very important. So now with NeuReality and IBM technology, the future of AI-based financial services can now be realized. And I imagine how it would be that every transaction we do with our insurance company or bank or whatever is going through all these at the same time in parallel. And for that, we have to change the way the system is built. We can't just keep throwing GPUs on the problem. I invite you to our booth, number 215, to join us, and we can share more about our different hardware solutions and software solutions. You can also visit us online. And thank you very much for listening. If there are any questions to me or Mukesh, feel free to ask using the microphone in the back. Come, Mukesh.
I was actually talking to your colleagues on the booth. An important between your platform and the end customers, I think there is work to be done with the ISVs, right? With the software vendors. So probably IBM is involved in that, because taking for example risk management, right? Murex is a very used platform out there in the thing. Have they worked with you? Are you planning on working with them? Or
definitely. So the way we work together is, first of all, we collaborate on the hardware level. We make sure that the deep learning accelerator and our IP is connected well, the software layers are connected. And then you will experience, if it's on IBM Cloud, you will experience it under the same Watson experience. So it's our responsibility to integrate with them. When we work with the Mukesh team, it's not only on how to connect the hardware, but we take real use cases for NLP, for computer vision, and we analyze the end-to-end system flow. So, Mukesh, you want to add something?
No, that's correct. That's correct. We are not in the business of making a chip. We are in the business of solving client problem. And that means we need to have the full software stack. We need to be able to integrate in cloud, and we need to have right ISVs part of this ecosystem as well. So that has to be comprehended.
All right. Thank you very much.
Thank you very much.